Okay, the first thing sensors we're going to look at are position sensors. And what do we mean by position? Huh? Yeah, where its object is located within a certain range. Yeah. Oops, sorry. So it's kind of like us. We can sense position, right, with our eyes, but you got to understand it's got to be within a certain range. Okay. So it's finding out where something's at, an object's at within a certain range. Okay, hopefully we understand what a sensor is now, right? We know that a sensor is a transducer, but a transducer doesn't have to be a sensor, right? It's about physical stimulus or stimuli into its electrical equivalent. The transfer function, which we'll play around a little bit, is the ratio between the physical stimulus and the electrical equivalent, which we'll have to understand if we really understand sensors. So this is the first one, position sensor. We're going to look at potentiometers, optical encoders, linear optical encoders, linear differential, linear variable differential transformers, which I think somebody brought up here last photoelectric sensors. We got a little lecture on this, ultrasonic and vision. So we can use any of these to sense position, right? So we got two types of potentiometers. We got what we call audio tailored. These are what we use. So we use for volume controls because our ears are not linear. So what we would like to do is we would like to turn the volume control up halfway and half maximum loudness. But if we did that with just what we call a linear pod, it wouldn't work. So it's what they call a linear pod, which means its opposition varies in a straight line. So anytime we use the term linear, it means in a straight line. So that means this pod, as we turn it, its resistance would change. And if it was a 350-degree pot, if it's a rotary pot, and then it was a 10K pot, that means when we turned it to 350 degrees, it would be 10K, right? You understand that? If we turned it halfway, then it would be what? It would be 5K, right? And that's what we mean by a linear pot. So a pot, a potentiometer is made up of three leads, always has three leads, right? And we have, and we just number them 1, 2, and 3. We refer to this as the wiper. I need to find the pot where you could actually, that we've taken a pot, so apart, so you can usually see it. So usually it's got a carbon film that goes around it, like this. And then if it's rotary, if it's a single turn pod, it can't always be single turn because you have to bring an input. And then what we do is we bring in an input and we hook it to a device called a wiper. And literally, when you turn that knob, it just does what? It just changes the ratio. Yeah. So what we can do is, depending on which one we reference to, if we reference to this guy, so if we put our comment on number 3, then what that means, if I turned it all the way up here, if it's a 10K pod, it would measure what? 10K. If we turned it in the center and it was a linear pod, it would measure what? 5K. If we turned it all the way down to the bottom, it would measure what? 0K. So we can literally get any opposite any resistance to the wiper. Now, what you got to understand between 1 and 3 will always be what? The size of the pot. So the resistance between 1 and 3 never changes. Where the resistance changes is between 1 and 2 or 3 and 2, depending on which one you reference as a common. I think if you put 3 as a common, I've always said I need to check that. Then I think the actual resistance to 2 actually goes up when you turn it clockwise. But that's all. Depending on which way you go, if you reference it to one of them, if you reference your common to one of them, then the resistance to 3 will increase when you turn it clockwise. If you reference to the other one, it would decrease, right? So whichever one you use, either 1 or 3, determines which way you turn the knob on your pot, whether the resistance increases when you turn it clockwise or if it decreases when you turn it. Now, what we're going to do, of course, is we're going to come over here. So this is basically a real good picture because it actually takes it apart. So we have a resistive element, and then the wiper just does what? Slides around that, right? So what we can do is we can treat a pot. We can consider a pot to look like this, right? Is relative to pin 2, right? I'm sorry. Or we can make it or we can make it look like a straight piece of wire, right? You understand? Or we can make it look what we call a voltage divider. And what we're doing is we're changing the ratio between the top resistor that I call R1. Let's just call R1 and R2. So that's what we're doing. We're constantly changing the ratio between those two resistors. So what that means is if I come over here and I put 5 volts at the top, so if I come up here and put plus 5 volts, then what can we do if I was to come over here and put a meter across 1 and 3, let's say? What would happen? Well, what if I turned it all the way up here? Then what would we get out? 5 volts, right? And if I turn it all the way down, what would I get? 0 volts. And then between the center, I would get something between what? Between 5 volts and 0 volts. Technically, we could have an infinite number of combinations, but this is going to be how accurate you can turn the pot. And the more turns, the more accurate the pot will be. So we have what we call a single turn pot. And actually, we make a single turn, but we still call it a single turn. And it has range in it. So we'll never get 360 degrees out of a single turn pot, right? Yeah. And supposedly I played around with these in DC, but I can't find any over there in the lab. But we might not be able to do it today because I can't find any pots. So we use potentiometers primarily to adjust the voltage. Y'all understand that? Yes or no? But what people don't understand is that we put a knot, and these are multi-turn pots. So the more turns you have, the more precise the pot would be. Does that make sense? So what we would do, let's say it's 350 degrees, which ours never measures that much, but let's say it's 350 degrees. And I come over here and I place 5 volts on that. Then how many volts could we get per degree? Up here, we're 350 degree pot. Okay, and I've got 5 volts attached to the top. What would be our volts per degree? First of all, what are we getting out? We're getting volts out. What are we putting it in? Degrees. What are y'all saying? Can't have 70. I only got 5 volts. Huh? I mean, the maximum I can possibly get. How'd you get that? That's exactly right. So anytime we calculate gains or anything, it's always out over in. So what we're putting in is what? Degrees. And what we do on a pot is we take the maximum degrees the pot will turn, right? You understand? And we divide that into what we're getting out. And this is what we call a transfer function. So a transfer function says, okay, this is we're going to take our output. We're going to see what output we would get relative to an input, right? Does that make sense? So what are we getting out? Maximum of what? 5 volts. And what's our maximum degrees? 350. So what would my transfer function be? 14.28 millivolts. Okay, so now I know my volts per degree, right? So if I came over here and put this out, that's not going to be 420 millivolts, because in Ohm's law, what we do is we ignore, to make Ohm's law work, we ignore the units. Because technically in math, this is volts, this is degrees, so this is not going to be millivolts. This is going to be millivolts per degree, because degrees and volts don't cancel each other out. Y'all understand? So this is why in Ohm's law, it's a ratio formula, and we drop volts and we drop ohms, we drop the units, because we would end up in algebra, we'd end up with ohms per volt, and y'all understand that. But we don't do it here. So this is 414.28 millivolts per degree, because that's usually what we do when we say per. So anytime we see this, we can use the term per, P-E-R. So per means for every one, right? You understand? So the correct way to write this, since this is not Ohm's law, would be 25. And what do we have up here? We have volts. So that is on top here. So it'd be on top here. So we'd say millivolts. And then what's on the bottom? Per degree. I just put D for degree, but that's the symbol. So that's what we're saying. We're saying 14.28 millivolts for every degree. So what would I expect my meter to measure if I set it at 35 degrees? So I've set this at 35 degrees. What would I expect it to measure? So I'd say I'd say my output, the out, would be equal to 35 times my volts per degree, 14.28 milli, and then that would tell me exactly what I should measure on the output of that pot. And this is what we call a transfer function. So now if I know what this means, then I can measure the output voltage, and then I can say, okay, that would be this degree, right? That makes sense? We take what's out and what we're putting in. So here, when you turn that knob, when something turns that knob, right now we're talking about us turning it. But that's a knob, guys. That's just the post sticking out. We can mechanically connect this thing to anything. And then when that thing moves, it's going to turn the pot. You understand that? So what we're doing is we're saying, okay, let's say I come up and measure 3 volts. What angle would be what my pot be at? So I'm measuring this out here. No, you're right. We can't have a milli-degrees. Okay, so transfer function is equal to what? In over out. So we arrange the formula and solve for out, right? I'm sorry, solve for in. So what would we do? We can put this thing in our little old formula wheel. I know the transfer function, so I can say transfer function would be over here, right? Up here would be in, and over here would be out. I'm giving you out, so what are we trying to solve for? In, right? Something's wrong. Yeah, but it's got to be out. You know, it's got to be out. What's that? No, what it is I'll have to figure it out in a minute. But what we do is we say, y'all like that. So what do we put? What are we getting out? Okay, so we're getting 3 millivolts out, right? So that's right, right? Then I know the transfer function, so we're going to divide this by 14.28 milli. There we go. I don't know, but my brain got washed up. So here's our formula, right? And it's a three expression formula. So that means that any three expression formula we can put in this little wheel that we usually solve for. So what's the transfer function equal to? Out over what? In. Okay. So I know the out. What's the out? What's the out? 3 volts. Good. What's the transfer function? 14.28 milli. And how would I solve for in? Yeah, so it'd be out, which is what? 3 divided by what? TL, 14.28 milli. I don't know why I was looking at it a while ago, guys. And then that should give us our degrees. Can be 200 milligrams. I can't take a whole and this is what you got to understand. I can't take a whole number and divide it by a fraction and come up with a number that's smaller than 210 degrees. Yeah. Yeah, that makes a big difference. Big difference. Yeah, and this is why if you understand this, then you realize you got the wrong answer, because that's a common mistake people make. So if you take a whole number and divide by a fraction, you will always come up and get a number bigger than what you started off with. You understand that? So what would it be? 200 what? I was right in front of me. I don't know what I was thinking about. That. My brain went dead. Y'all ever do that? So let's do this. So the transfer function is equal to what? Out divided by n. And then we could put it in that little thing that you learned in what? DC. Now, if I want to solve for n, then it's going to be out over the transfer function. If I want to solve for output, it's going to be equal to the transfer function times n, right? Understand that? Let's do another one. What would be the, let's say I got 1.2 volts. If I measure 1.2 volts, what would be my degrees? You don't have your calculator, Kevin? Right, but it all depends on what we're working with. On pots, that's yeah, right, because we have a bunch of things that change that vary their resistance with what they measure. Yes. Yeah. So normally we use rheostats to establish a current, and we use potentiometers to set a voltage. But like I told y'all, to wire a rheostat, to make a pot act like a rheostat, you got two options. You can ignore one of your pins, and you can do it like this, and then do it like this, measure from here to here, and this would act like a rheostat. But that's not the preferred method, because what you have is you have an antenna sitting up here. So you got a lead, a wire just sitting up there with nothing hooked up to it, and it'll be very, very noisy. So way you're supposed to hook a rheostat, a pot as a rheostat, is you're supposed to take the wiper and connect it to one end. And then now you don't have an antenna, because the end would come up here, and then I guess I should put it like this. So you're going to see pots wired as rheostats a lot. Kelvin, if you're going to sleep in my class, okay. Well, so you already know all this? Okay. So everybody okay? So multi-turn pots, we have 10-turn pots, so that would be 360 times 10, right? You understand? So then our transfer function would be what? Would be our input voltage over 360 times 10. So now we're getting way down in the millivolts. So the more accurate you need to be with your what these things are measuring is you may need to go either to a 10-turn pot or to 5-turn pots. You can get 5-turn pots. The only one we're going to deal with is what we call a single-turn pot. I don't think I've got any of these over here. So this is a pretty good animation of what a potentiometer does. So let's see if we can figure this out. So this would be a pot connected directly to the shaft of a motor. So instead of me turning the pot, instead of me turning it, now the motor turns it. And then what's going to happen is the pot is going to give us a voltage that's going to be equal to the degrees of the motor, right? Does that make sense? Okay. Well, I just passed the pot around. We got to bring that center leg in there. If I've got to bring that center leg in there, yeah, if I've got to bring this center leg in there and hook to the wiper, then we'll never get 360. Yeah, because we got to bring that wiper in there, right? What your multi-turn pots do, I don't know if they'll show the inside. So here on this linear pot, here's your wiper. But what we do is when we turn that thing, it's got a little worm gear in there, and it moves it up and down. So this is why we can get multiple turns out of that guy, because we don't have to bring that connection to that center lead in through the other two, right? Does that make sense? So this is the feature most multi-turn pots work on. We saw one that actually it was actually a single turn pot, but they actually geared the wiper. So I don't forgot. I think for every 5 turns, this thing would move the distance of a normal 1-turn pot would do. And these are more precise, right? You understand? Multi-turn pots are more precise. Well, it wouldn't be called a single-turn pot. It'd be called a 5-turn pot. Yeah. So what we're going to be doing, they called it a single-turn pot, but you can't get a whole turn out of it. So single-turn pots, you'll never get 360 degrees. But the way the 5-turn pots are set up is they're set up where you turn the knob multiple times to get it to move, right? So what would be the transfer function on this? We got 10 volts. We need the size of the pot. No, we don't. By the way, the size of the actual ohm value of the potentiometer is not really relevant because, but the problem is that the bigger the pot, then you're going to have more ohms per degree, which means it's going to be harder to set it, right? Does that make sense? So a 1-turn pot would be more accurate a 1K pot would be more accurate than a 10K pot. You understand why? Yeah, because you have less volts per degree. No, well, it'll be close because it's got a tolerance just like your resistors. And usually the tolerance on most pot is the plus or minus 10% on most pots that I've seen. So that means, but when you use it as a position sensor, the plus or minus 10% don't really make any difference because you're dealing with degrees and volts, right? Does that make sense? So here it should be a lot more accurate than. So what would be the transfer function on this guy? Let's say 350 degrees, which is what they say. 350 degrees, so we take the maximum voltage you can ever get out, which would be what? 10 volts, and we divide it by the maximum degree. So we take what? We're getting what out? 10, maximum amount, degrees, 350. And what did you get? 57 millivolts per degree. Okay. This is not Ohm's law. This is actually real algebra, right? 350 degrees. It's got to be a single turn pot. If it was a 2-turn pot, it would be 7, maybe. It depends on how the wiper moves, how they move the wiper. Most of your multi-turn pots, you get the full range of the pot because they don't bring that center leg up through the center. They either come across the top, right? You understand? So either way it goes, the degrees will be given. Yeah. Okay. Whether they call it, if they call it a single turn pot, but they give it 700 degrees. It's not a single turn pot. But I'm just saying, hypothetically speaking, will we go with the actual single turn or we go with 700 degrees if it was given to us like that? No, but you're not understanding what I'm saying. If you had a 2-turn pot, then you would use 2 times 360 degrees. If you had a 5-turn pot, then you'd use 5 times 360 degrees, and that would be your degrees. So there will never be a single-turn pot that is 720 degrees because it's a circle, right? I understand. Normally. Because normally if it's more than that, then they don't use that the conductor coming into the center. So if you look at this one right here, this conductor does not come in. So I'm going to turn this little knob right there. Well, that sucker is turning a worm gear. This guy's turning the actual measurement, the actual pot there. So what that means is that we're not sacrificing that space to do what? To get this center lead through. Because the center lead is not come. See what I'm saying? Yeah. Yeah. So what we're saying on this one right here, we're not sacrificing. So this lead comes up and connects to this worm gear right here. Yeah. We got to bring that center lead through. And you can see it real well right here. So I got to bring that center lead through because of the way the pot is designed. Right? You understand? But multi-turn pots, normally we don't bring a center lead. We come like across the top, right? So we don't lose that. So like we're saying, there will never be a single turn pot. I've never seen one that's 360, but it wouldn't surprise me. So what you do is in fact, these right here, we're saying 350 degrees. Are we going to get 350 degrees out of that? Probably not. So what we're going to do when we do our lab is we're going to take a compass and put it on the bottom of that sucker, and we're going to turn it, and we're going to measure the what? The degrees that we can get out of it. And that's what we use for our transfer function. And that way it's like back in DC. What did you do with all your resistors before you put them in a circuit? You measured them, right? And then in your calculations, you didn't use the color-coded value. You used the what? You used the what? The measured value. Because you were trying to prove that what? V is equal to I times R. And but after that, once you get out of that class, all your other classes, we don't measure resistors. We understand that if we use 350 degrees, we understand that it's going to have a plus or minus 10% tolerance on it, right? You understand that? If I needed it to be extremely accurate, then I would measure the degrees. And measuring degrees is not hard, right? You understand how we would do that? We would take we've got one. I'd print out a compass. I would put the pot on there. I would turn it all one way, and I'd put that on 0, and then I'd turn it until it stopped. And I would literally measure the amount of degrees that pot actually went to. And then that way, your measurements and your calculations would be really close, right? You understand? So that's what we're going to do in our lab as soon as I get some pots over, find some potentiometers. I got plenty over in another class, but I took for granted since y'all did it in DC and we do DC over here, that we'd have some potentiometers over here. Everybody okay on the 28.57 millivolts per degree? But you're right. You got to know what? You got to know that right there. A pot is applied with 10 volts. Is set to 82 degrees. The range of the pot is 350 degrees. Calculate the output voltage. Everybody do this. Just calculate out. We've already got an answer. Jacob, what'd you get? Jose, what'd you get? You got who's back here? Kurt, what'd you get? What'd you get? Alexander, what'd you get? Okay. Jalen, what'd you got? You're just saying that because I wrote it down up here. First of all, we need to calculate the transfer function. What are we getting out? Yeah, so the transfer function would be equal our out, which we're getting volts out. We're putting, so normally what we use is we use the maximum out over the maximum degrees because we know that's going to equal that, right? That's degrees, guys. That's not. All right, I brought up the answer. So 0.28 or 28.6 millivolts. And then we take that and multiply that and come up with this guy right there. Are we okay? The problem we have with most pots is we have to be really careful with what we load them in. So normally what we want this thing over here is we want this, oh, wrong way, Rich. We want this guy that it's feeding to be real high R. Multimeter we have no problem because what's anybody know the resistance of their multimeter? No, your opposition. So anytime we hook something in parallel, everything has an opposition, right? You understand? So what we're saying, and this became So if I came over here and this was a 10 mega ohm resistor, and then I come over here and hook my meter in parallel with that, and then I put voltage on this thing, and then I try to measure current. Let's do this a little different so we can let's do a voltage divider. So let's say this is 10 mega ohms. Oops, mega ohms, Rich. And then this is 10 mega ohms. And then I come over here and put 10 volts on there. What would you expect to measure right there? Yeah, 5 volts. But it's not going to measure 5 volts. Can anybody tell me why? It's going to measure less, guaranteed. No, the problem is that meter is a load. As soon as I put that meter right there, I put something in parallel with that resistor right there. So your meter has a load. It is a load. One of the things that you do when you do your meter certification, everybody in here got that meter certification? What was one of the things you did? You measured the resistance of that meter. You measured the resistance of that meter when you put it on volts. So normally it's about 10 mega ohms. Well, if I come over here and hook my meter up there, then what I'm doing is I'm putting a 10 mega ohm resistor in parallel with a 10 mega ohm resistor, and all of a sudden this right here is seen at 500K. So what I'm saying is you can never, we had a high resistance circuit, we called it a high impedance circuit, out at US Steel. It came off electronic, called a mag amp. And he went in there and he wanted to measure the output of that mag amp with his meter. As soon as he put that thing across that mag amp, the whole line shut down, just like that. Boom. Because he didn't take in consideration that when he put that meter in parallel with that mag amp, the resistance dropped way down, and that sucker thought it had too much current flow into the motors. So I thought the motors were overloading. What did it do? He shut the whole line down because he didn't take in that consideration. So what we're saying, if I come over here and I have a 10K pot, and I come over here and my meter had 10K ohms of resistance, then all our calculations is out the way. Because now what I'm doing is I'm setting up a circuit like this. So no matter what I do, if I come up here, I've got a resistor in parallel with this guy right here. So now all our calculations are out the field, because that's no longer just a pot, it's a pot that's actually loaded. So what we have to do when we play around with the potentiometer is this load. Now if I come over here and this is a 10K pot, if this right here is a 10K pot, and then my meter that I'm hooking this up to is 10 mega ohms, then by George, there would not be enough error that we could totally ignore, because now I'm putting a 10 mega ohm in parallel with something that's going to be less than 10K, right? You understand? We call it a 10-to-1 ratio. If we have a 10-to-1 ratio in a parallel circuit, normally we can ignore the big guy because it just don't hurt us enough to cause any problems, right? You understand? So what we're saying is that for a pot to work, this load that this guy feeds into has got to have a really high input resistance. If it does not have a high input resistance, then we've got a problem. So that means if I had a 10 mega ohm pot and you put your meter across that wiper, then all your calculations are going to be out the whack. But as long as this would be another advantage of using a pot that has a lower resistance, right? You understand? So it wouldn't have near as much loading effect. We call it the loading effect. So we have electronic devices, guys, that has almost infinite. I mean, it's real high. We're talking about in big ohms, and these are called operational amplifiers, which we don't have time to get into this class. But these operational amplifiers have extremely high input resistance, and this is the problem they have. So here we would say this is 10 volts, but in actuality it's what? 4.88, because the thing I'm trying to hook this thing up to has a low resistance. So this is why these analog inputs on these program controllers and these devices, these analog inputs have extremely high input resistance. But you got to remember, as soon as you put your meter across that, you're adding something in parallel. And this would be a reason why your calculated values and your measured values might not be exactly the same. And we call it the loading effect. We're not going to have any problems because we're going to use a 10K pod. I think we're using a 10K pod in your multimeter. We can assume it's got what on your volt scale? Probably around 10 megohms. But you can measure that. How could you measure that? How'd y'all measure it back in DC when y'all did y'all meter certification? The ohms. You put the meter on volts, and then you took an ohm meter and you measured across that thing, and you measured the input resistance of your meter. Yeah, it was 14. I think that thing measured around 14 meg. So that guys are really, really good as far as not loading what we're trying to measure. But I don't even think, and we were using, this was back before we had digital meters, guys. I'm telling my age. We had no digital meters. So we had these analog meters. Sorta, but we had I need to bring it in. I still got it, guys. It's a Simpson 360. And that was the meter. That used to be the meter. It's kind of like Flux now, but Simpson meters were the meters. And that's what we had with the Simpson 360. And the problem is the actual resistance changed depending on what voltage scale you had on. So the lower the voltage scale was, the less resistance the meter had. So basically, it was nothing but a voltage divider. So when you switch the switch on that one, you just switched to a different voltage divider. So real interesting. So here's using this Simpson 360 when we shut down the line. That's another story. So Dennis Ramsey, he used to teach with this. Transfer function. So here what we do is we have a potentiometer connected through a gear. Now, what do we use gears for normally? That's what we use the pot for, but what we're doing is we got a gear right here, right? Well, it does one of two things. If work equals a force times distance, then what happens if you increase the distance, and you're going to have, in work in equals work out, right? You understand that? And then it's times efficiency. That means if work is equal to force times distance, if you increase the distance, you're going to have to do what? Just to 4. So we use these things as either speed multipliers or we use them as torque multipliers. If the torque goes up, then the speed goes down. If the speed goes up, then the torque goes down. So here, all we're trying to do is we got a big gear feeding a little gear. So what is this guy going to do? Is it going to increase speed or is it going to increase torque? Yeah, speed. So that means also, so what happens is that when we move this 90 degrees, that's going to move 3 times. That's going to move three times this guy right here, right? Understand? Does that make sense? So 90 degrees over here would equal the watt over there, 270. So what I would have to do is I would have to figure what I need to do. I'm taking my measurement right here. Right? So this is going to be where we're going to take our measurement. But over here, 270 degrees actually equals what over here? 90 degrees. Huh? Well, what we're saying is that if this guy right here turns 90 degrees, this guy's going to be 90. The pot's going to turn 90 times 3, right? Which would be what? 270 degrees. That makes sense? Yes or no? Yeah, 3-to-1 ratio. So we don't have 350, but let's say at 270 degrees, we get 6 volts. So let's say I measure 4 volts. How far did my motor turn? 270, I'm sorry. 270, we got 6 volts. That's all we really know. We don't know if it's a multi-turn pot. All we know is 260 degrees, we get 6 volts. That'll be enough to give us our transfer function, right? Right? Yes or no? Transfer function would be what? Well, we get out at what? What's that? Millivolts per degree. So what did I say? What angle did I say? Huh? Did I say 45? We can't make 45. 45 would be too easy. Oh, dang it, Rich. So let's say, what would I get out of my pot if I was sitting at 20 degrees? 20 degrees, Rich. Well, first of all, I take 20, and then I multiply it times 3, which would give me what? 3. Yeah, thank you. I get what? 60. Okay. Yeah. Y'all understand? Because when this guy here moves 20, this guy up here moves 3 times that, right? You understand? So then I take what? Yeah, 60 times 22 millivolts. Is that okay? Everybody get that? Everybody get that? So force is going down, distance has to go up, right? So that's because we're taking a big into a little. Okay, guys, y'all go ahead and take a break. ADCs, analog to digital converters. So we need to understand that, especially in sensors, analog sensors. All the sensors, the only analog sensor that we're going to do a lab on is going to be the potentiometer. All the other sensors that we're going to work with this class are all right. But hopefully you understand why we would need analog to digital conversion. There's some things that you just can't do digital, like trying to maintain a constant temperature, right? So your air conditioning system, HVAC system you have in your house, that sensor is analog. So actually, we bring this spec into the programmable logic controller. Programmable logic controllers are digital devices, but the new ones used to, if we wanted analog, because most of the stuff we're dealing with out there is digital, right? You understand that. But then what happens if you had a program controller that needed analog, then what they would do is you would have to buy another module for your, you have to buy an analog module for your PLC. but most of your current new PLCs come with an analog capabilities. Normally it comes with analog in, and you have to get analog out. The 314s that we have, the Siemens 314 PLCs, which we'll get over and look at. We did get I took my class in there yesterday, and that big compressor had stopped working. So it's been a bad day for all those guys. But the input to the it's got I think it's got 5 analog inputs. It's got 5 analog outputs on it. And I think some of the analog inputs are current loops. I have to go back and look. But analog to digital converters, and what we're going to do is we're going to take an analog value and we're going to convert it over to a binary equivalent. And then that binary equivalent is going to mean something, right, inside a computer program. So we have 3 types that we'll look at. The main one that we usually look at is this dual slope integrating amplifier. This is the one that's used most often. I mean, A to D converter. This is what your digital meter uses. This is what most PLCs use. We'll look at that one in a little more detail. This is the first one I ran. It's called flash converter. So what it did is it set up a voltage divider. So how many of those things we got? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8. So what we do is, let's just say my input was going to be from 0 to 8 volts. And the way all these resistors would be exactly the same size. If they're exactly the same size, it means they drop exactly the same volts, right? So 1, 2, 3, 4, 5, 6, 7, 8. So we call these little comparators. So they only go true when this input right here matches this input right here. So what would happen if I was from 0, if it was 0, 1, 2, I mean, if it was 0.5, then this guy here wouldn't do anything. The only thing that's going to happen is when my input gets up to 1 volt, then this guy right here would say, okay, it's matched me, and it would send that up there. And then this guy right here will give me a binary code for a 1. Have y'all played around with binary at all? Yes, no? No. Yeah, well, binary, we have bits, right? We call them bits. And when we count, and we start off with 1, then what comes next? 2, 4, 8, 16, 32, 64, right? Like that. Yeah, 128, 256, 512, 1024, 2048, 4092. 8,192, 60,000. So what happens is this guy would come into this decoder, and it would say, oh, what did I have on the input? I had a 1. And then anything between, oops, what did I just do, guys? So anything between 1 and 3, anything between 1 and 2, it won't notice, right? You understand? So it wouldn't. If you had 1.2, it would still be 1, 2.3, all the way up until it hit what? 2, and then this guy here would trigger, and then my output would go to what? It go 2, right? You understand? And then then it don't recognize anything between what 2 and 3, but as soon as it got to 3, then it would trigger this guy, and this guy right over here would give me a 3. Yeah. So this guy right here, we call it a flash converter, and it's really fast. This thing is instantaneous. It is instantaneous. So these guys are extremely fast, but it takes a lot of hardware to make these things. I mean, a lot of hardware. So you'd have to have one comparator circuit, and the more resolution you wanted, the more you would have to have, right? You understand? So right now I got 8 combinations. If I wanted 256 combinations, then I would have to have 256 comparators. or 255, because we start with 0. So the more comparators you have, the more accurate it is, but the more expensive this becomes. So these flash converters, these are extremely fast. But the problem is that we're going to have problems. They take a lot of hardware. They're going to consume a lot of power, right? Every one of these circuits that you put in there, they're going to require the current to run that circuit. So there's got to be a better way, right? But these are fast. So if I needed instantaneous conversion, then this is the guy you would have to get to. Is this what your meter uses? No way. Your meter is not instantaneous. Your meter is slow. That's why every one of your meters has a what we call a frequency response, which means if you try to make it measure something above that frequency, it can't do it because it don't have time to convert it. So the big advantage of flash converters is they're what? They're instantaneous. Yeah. So if I'm going to reduce the cost, then we're not going to use this guy. The other one that we're not going to fit, so flash converters. So if I did 250, if I wanted 256 combinations, then we'd have to have 255 comparators. Low resolution, very expensive, a large amount of power. The only advantage to these guys is they're what? Fast, yeah. Yes. Who's the guy that just broke the? He just run the marathon in less than two hours. You know, I remember when they were saying if you beat that's a 32 mile run, right? Isn't it what a marathon is? 26 miles. Yeah, I'm sorry. It's from Olympus. Wasn't it? 2 hours. He did in less than 2 hours. It was a big deal when I was if you broke the 3 hour, but now that guy's knocked a whole hour off of 20. I forgot. Yeah. 2 hours. Running, a human running it. Yeah. That day. If I did a marathon, it'd probably take me 4 or 5 days. Well, the other one we had was what they call a Sigma Delta. Of course, I could do it on a wheelchair, right? Yeah, but I'd have to get one of those fancy wheelchairs. Oversampling. This guy right here, this guy's real fast. I mean, it's not as fast. Another problem we have is this guy gives us what type of output? 0, you know. Yeah, but they're one after the other. So we're not going to look at this very long. High resolution, no precision, right? No precision external components needed, but it's very slow because it's got to do a lot of sampling. Now the next one is this is what we usually use. This is called a dual slope integrator. This is what your meter uses. This is what PLC uses. This is the primary analog to digital converter. Yeah, dual slope. Now, why they call it a dual slope is they sample. What they do when the input comes in, they're going to charge a capacitor. And they're going to let it read the input for a certain amount of time. So it switches over, brings the input in, charges a capacitor. So it would come up and do something like this. So the capacitor charges. And what's nice about it is it gets rid of all this variation on the input because the capacitor is going to charge at a steady rate. And then it's going to hit this point right here. So it's going to charge that capacitor over a certain amount of time. And then what it does is it switches over and discharges the capacitor at a certain amount of time. Yeah, it does. And this is why your meters are real slow. So your meters, you can actually see those things when you put it into a circuit. You can actually see them updating, right? So for a little while they'll go blank, and then all of a sudden they'll come up and show an output because they're trying to do this stuff. Then what they do is once they switch it over, they start a counter, and the counter just starts counting until it discharges back to 0, and then the counter stops. Well, this slope right here would be proportional to the input signal, and this is the way it works. And then all they're doing is just displaying the output of those counters. And then when it gets through, it would do the what? It would do the whole process over again. And this is why a lot of your meters have added an analog output on it. It's got, if you remember the Snap-on meters, it had a little bar on it because this integrator is very, very slow. So if we were looking at a varying input, and I think y'all did that in that lab, you actually put a varying input on there, and your meter just did what? It was all over the place because it can never integrate before the voltage is changed. So this is this is by far the most phenomenal thing, because one thing we actually get a count that represents the actual input voltage, or the input quantity, whatever you're trying to measure. Advantage input is averaged, greater noise immunity over other ADCs, high accuracy if you get them timed. Disadvantages are what? Yeah, so what we're going to do is we're going to take this and we're going to convert it into a binary number right out of our counters. So what that means, if this guy right here, it's got a 10-bit analog to digital converter in it, so 10-bit. So that means I can represent a number between 0 and 1023. Y'all understand where we get that? Yeah, it's 2 to the 10th, which would give us 1024. But why is 1023? 0, yeah, 0, right? But if I had a 16-bit, then I would take that analog quantity and I would split it up to 65,535, right? You understand that? That makes sense? Well, let's say the maximum, what we'd say, okay, let's say I'm putting an analog value in and the maximum is 10 volts. So I'm putting what in? 10 volts in. And then what's my maximum count? Okay. So this would give me my volts per count, right? Does that make sense? So what we got? Per count. Everybody get that? So what count would I get out if I brought 3 volts in? Doing is we're putting volts in and we're getting count out. It's out over in, right? Out. There you go. Thank you. So we have what? 300 what? Yeah, I'm trying to. Go ahead, Alex. Good. 102. 1.0. Okay, so Alex was giving me the whole answer, right? Yeah. Yeah, he did. And this would be counts per vote, right? So we're trying to solve for count. So what's it going to be? It's going to be the transfer function 102.3 times the votes, which would be what? 3. And then this is what Alex gave us. Yeah, that's counts per vote. That's our transfer function, right? I guess y'all doing it. 1023. Well, yeah. Well, what you do is you take your maximum count out. Our maximum number we can get out is 1,023. We get 1,024 combinations, but the maximum count we get out is 1,023. Why? Because 0 is one of your counts. But you'll find out on 1,023 and 1,024, it's not going to make that much difference, right? You'd get the same answer. Go ahead, Brian. Yeah, so I gave y'all. Yeah, yeah. Well, you have to know the in and you have to know the out before you can calculate transfer. Yeah, well, the problem is I didn't. I said 10 votes, but you're right. I didn't write it up there. Okay. This is pretty standard, by the way, on PLCs. 10 votes, 0 to 10 votes is pretty standard for the analog inputs. This guy right here, 0 to 10 votes. Well, if we did the votes per bit, right, we'd switch that thing around. Yeah. But you should come up and get basically the same answer, right? Yeah. Then you have to convert it over, right? So it's best to just say, what are we getting out? Well, we're getting counts out. What are we putting in? We're putting votes in, right? You understand? Then we came up with that, and now we know this is going to be 307. Now, what's nice about programmable controllers, even though it's a binary number, they display the decimal equivalent for you. So we basically don't have to know that it would be whatever 307 would be in binary, right? You understand that? Because it does that for you. That makes sense? Yes? No? Well, what Alice was talking about was trying to calculate how many votes you had for every bit, which we don't really need to do, right? You understand? Because we got the maximum number of counts, and we've got what voltage would be if you got that maximum of times. So we know on this guy, and this is another thing we need to look at too, guys, is that problem that I had is I've got a 10-bit DAC, I got a 10-bit digital analog converter inside this PLC right here. and it only recognizes things from 0 to 10 volts. So y'all figure this out for me. My A to D converter only recognizes voltage from 0 to 10 volts. But when I hook my pot up, so what I'm going to do is I'm going to bring this in. This is going to be my input. I want 10 volts right here, but all I had up here was a plus 24 volt supply. So how can I take 24 volts down to 10 volts? No. These are DC, guys. These are DC. Let me put a new slide so I can get this. So this is a good problem. So I got a pot, and I want 10 volts right there because I'm going to bring this into the input of my PLC. And all I got up here is a 24 volt supply. 24 volts. No. I got a 24 volt supply up here. Let's say it's a 10K pot. No, I've got a 10-ton pot. I want 10 volts on the top of it, but all I've got is a 24 volt supply. I've got a device that drops a voltage if I put a current through it. What is that device? Okay. So what we'll do is we'll come up here. I know all I have to do is just put a resistor right there. Okay. But I got to know the size of that resistor. Or the ohm value. I ain't using the size because the size would be the physical size. So we need the ohms. So what do I need to know to calculate? What do I need to know to calculate voltage R? So okay. So R is equal to V. What? We're calculating R. Okay. Do I know anything? How can I calculate current? Not 24 by 10K because I want 10 volts here. I don't want 24 volts here. I want 10 volts there. I want this guy right here to drop 10 volts, right? I want to drop it 10 volts at 10K. 10 volts at 10K. So I would be equal to what? I want it to drop 10 volts at 10K. 10 volts at 10K. Everybody okay there? Okay, so it's a series circuit. So, okay, I want this guy here to drop what? 14 volts at the current that I calculated right there at 1 milliamp. Okay, so R is equal to what? It's going to drop how many volts? 14 volts. What current? 1 milliamp. You're dropping your zero again. You're dropping some zeros. That's 1 milliamp. So understand, this is, you should understand, if I take a whole number and divide it by a fraction, my answer is going to be bigger than what I started off with. 14K. So we came in here one time, we had a 26 volt relay that we were going to use. All I got available was 120. I had a 26 volt, 100 ohm relay, and I wanted to hook it up to a 120 volt supply. What did I put in series with it? resistor. How did I calculate it? 24 volts, 100 ohms, right? Calculate the current, chose the resistor to run that relay. Of course, we need some more stuff about what else do we need to know about a resistor besides its ohms? Tolerance we usually kind of ignore because the voltage is going to be okay, right? But we do need to know there's two things that are very important. You know, the watts. So if I'm going to use a 14K ohm resistor, what wattage rating should it be? Yeah, 1 milliamp, 14K. No, we use the voltage that the resistor is dropping. So it's not dropping 24 volts. This guy right here, this guy's dropping 10, right? 10 volts, right? Okay. How much is this dropping? 14. So when you calculate the wattage of a resistor, you don't calculate the voltage applied to the circuit. You calculate what voltage that resistor drops, right? You understand? And that's a common mistake too. What wattage rating should I use for that resistor? 14 volts times 1 milliamp comes up to be 14K, yeah. Times 1 milliamp. Yes, you're right. Equals what? Good gracious. Is that right? Everybody got that? No. V is dropping 14 volts. So we got two formulas. We got power is equal to V times I, which would be equal to 14 volts. Oh, y'all messed up then. 14, that's why y'all got me. 14 volts times 1 milliamp. No, y'all kept saying 14K, not me. There you go. Thank you. Or I could use what? I could use V squared over R, 14 squared divided by 14K. So you could use this one. Huh? Yeah, since you got both of them. And then another one would be equal to I squared, which would be 1 milliamp, 1 milliamperage squared times R. This is stuff y'all should know. Not for Ohm's law or Watt's law. So you need a formula sheet with that on there? It depends on what you want to solve. So transfer function is equal to out over N. So what you get out divided by what you put in, right? Right? And so potentiometers, everybody okay with potentiometers? There's a lot more to it than you did in DC, right? Yeah. So I'll see if I can, so that's what this is right here. This is one of our analog inputs. And I'll see if I can, I don't know if I got a program out there yet or not. And you'd see, so right now I'd have a problem because the power supply on this guy is a 24 volt supply, right? You understand? So I need to find about a 14K resistor to hook up in series so I'll get 10 volts, right? And we'll see that. Oh, I've got a box over there that's already set up. Okay, the next one we'll look at is optical rotary encoders. I don't know if this is covered in the textbook or not. Optical. Yeah, we're ADC that we're going to look at that's primarily used is that dual slope, right? And the problem with the dual slope is what? The biggest problem is that it's slow, but it doesn't take very many parts. Optical rotary encoders, we have two categories. We have an absolute, and by the way, so what's today? Wednesday. Monday, make sure you bring your meter in and make sure you bring your safety lights in, right? Because we'll be doing we'll do the lab on the potentiometer. Two categories of optical rotary encoders. We have what we call absolute, and we have an incremental, and we're still in position sensors. In the subcategories, they could be rotary or they could be linear. So this is an absolute encoder. What we normally have is these things are usually made out of metal, and they'll have slots cut into them, or they're usually made out of plastic, and then they'll have use what we call light emitting diodes. So what we do is we got a light transmitter on one side that transmits a light, and then we got a receiver on the other side that sees when the light is there, right? So what happens is the black would block the light, and then the clear would let the light come through. And then what we do is these LED. So what we do is we'd have one LED and we'd have one transmitter and one receiver for each band. And as this thing turns, it's either going to block it or not block it, right? You understand? Okay. So right now it would be in the 0 position. So if we turn this way, it's going to cover up this guy, and when it's covered up, it's going to see it as a what? It's going to see it as a 1. So that would be a 1. This right here would be a 0, 1, 0, 0. That would be a what? 2, right? This would be a 1, 1, 0, 0. That would give me a what? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if I've got a 4-band absolute encoder, then that means we can represent positions from 0 to 15. So when this thing is, whatever I'm trying to sense the position of, this guy would be connected to it. And as this thing moves, this encoder does what? Turns. And it gives me a binary number that tells me exactly where that thing's at. Now, what's the problem? Well, the problem is that I can only sense 15 positions. Right? You understand that? So what if I wanted to sense 32? Well, I would come out and I'd have to add another band, right? I'm sorry, 16. I'd have to add another band. I'm sorry, 32 would be another band. And then if I wanted to do 64, I'd have to add a what? Another band, right? You understand? Yes or no? Yeah, powers 2. So every band we would double the number of counts that's available to us. Now, what's nice about an absolute encoder is that you could have this system out there, and you could turn that sucker off, and you could come back the next day and turn it on, and your controller would know where that thing was at. It would be able to know exactly where that thing was at. But what happens is the more precise we want to make this thing, the more bands we got to add, right? You understand? If we try to make it the same size, that means these little bands are going to get so small that we're going to have a hard time sensing the actual position. So these things are really, really accurate, but they don't have a real long range to them because we have to keep adding what? Bands, yeah. So this would be an absolute encoder right here, and this would be the actual sensors. This would be 1, 2, 3, 4. I see that's not a band, Rich. 1, 2, 3, 4, 5, 6 bands. So how far can we go with this? 2 to the 6, which would be, yeah, so this guy could actually be 64 positions, right? But if we stop this thing, no matter where we stopped it, if I could do that, then it's going to do what? It's going to remember its count, right? Okay. This would be a linear encoder. This is only 4-band, so this would give us only 16 positions. Yes, but they don't use an absolute encoder. Those suckers have thousands of steps. I mean, we're not talking one. Them suckers have thousands of steps, right? So that means that if I use an absolute encoder, these suckers would have to be out that far, right? You understand that? But they trick us off. So what we primarily use, counting in binary. So counting in binary, right? Y'all see how this goes? Okay. Now, how many? The problem when we count in binary is that we have a term called propagation delay. So what happens is the more counts that change, the longer it takes to go through our counters. That's actually doing the counting for us. So what we notice, if I go from a 0 to a 1, how many bits had to change between a 0 and a 1? Yeah, just 1. How many changed from a 1 to a 2? 2. This guy changed from a what? And this one changed from what? Okay. And now how many bits changed between here? Yeah, 1. How many changed between a 3 and a 4? 3. And you can see what's happening with binary is that, for one thing, the counts are different every time. They change a different value every time, right? And the bigger the count, the more changes you have, the longer it takes to propagate through the counter. So what is a code? Yeah, what's code? It's when we use something to represent something else, right? Okay. So they came out with a code called a gray code, which is a high-speed counting code, but it's a code. So code means this is not binary. This is a number. This represents a number, right? You understand that? I don't know if I said that right or not. So this is the count. This would be 1, this would be 2, this would be 3, 4, 5, 6, 7, 8. This would be what? 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. We can keep going. Now, if I came over here, I'd say, well, heck, I'm sorry, I started off wrong too. So y'all let me get by. Y'all let me get by with a lot today. Where do we start counting from? Yeah, thank you. I started at 1. I started at 1. On my side over here, this would be 0. This would be what? That'd be 2. You say, wait a minute, that's not a 2. But it's not a binary number, it's a code, right? So that pattern represents the number 2. It's not a binary number, it's a code. Y'all understand that? This would be the gray code for a 3. This would be a gray code for a 4. This would be a 5. This would be a 6, and this would be a 7.
Okay, so binary, but that's the code. But the binary number for 0 would just be 1, right? Because that's why I'm getting lost there. Because there's 8 numbers that's up there for the binary.
No, it's not binary. It's a 1 and 0 code that represents a count. This.
For my saying, the zeros, that's 8 numbers. If we put that in binary instead of this code, if we had all that in binary, that'd be 8 numbers in the binary.
Yeah, binary is a number system. This is a code.
Okay, I'm just trying to make sure I'm understanding.
So this is not a binary number. This is a code that represents a number, right? So this pattern represents a 0. You say, okay, that's the same as binary. This pattern represents a 1. I mean, this pattern represents a what? 2. It's not binary, it's a code, right? This pattern represents a what? A 3. This pattern represents a 4. It's not binary, it's a code, okay? But look, for the code for a 0 and a code for a 1, how many bits change? From a code for a 1 and the code for a 2, how many bits change? 1. This was a 1 here, and what is it still? A 1. From the code for a 2 and a code for a 4, how many bits change? Yeah, here's 4. From here to here, this is the same, this is the same, this has changed. From this code, you said how many bits change? Just 1. All right. This one stayed the same. This one stayed the same. This one right here changed. So no matter where I go, if I go over here, how many bits change between? So that one stayed the same. That one stayed the same. This one changed. This one stayed the same. This one stayed the same. Yeah, so gray code is a code. It's not a binary number system, whether you count up or count down. So let's go this way. How many bits changed? This guy didn't change. This guy didn't change. This guy changed, right? This guy didn't change. This guy didn't change. So on the gray code, no matter which way you count, you only have how many bits change? 1. We could go through this whole chart and we'd always see what? 1. But it's a code, which means you as a human, you can't take this code and say, okay, how would you have to do that? Well, you would have to look up with a chart unless you knew how to convert it over. There is a technique to convert it over. But what you need to understand is that some of these high-speed counters are going to count in gray code. So gray code is a counting code. How many bits change between each count? 1. It's a high-speed counting code. So some of the counters you're going to run out there is gray code, which means if you want the number, you're going to somehow have to do what? Convert it back over. Huh? Yeah, you could Google it. You can say gray code to binary, and it would come up. They've actually got, there's a place over there where you can enter your gray code on one side, and it does the conversion for you. Yeah. So that was this is a grade code, absolute encoder right here. So you can't actually use the binary anymore, right? You understand that because it's code. So you're going to know that, guys. So, and this is an absolute encoder. How many bands? Oh, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bands. This is band. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm sorry, 10 bands. Oh, I'm sorry, 11 bands. No, this might not be a band. I think this is a 10 band. I don't think this right here is actually a band. I think this is the first band. Because see the big station right there? I think this is 10 band. Which to give us 1,024 positions. It looks pretty anyway, doesn't it? You ever say, what is that? You say, well, that's an absolute encoder, right? So somebody's going to, when you have those interesting tattoos, somebody's going to ask you what that is, right? So this is actually an absolute encoder. This is made out of metal, and the holes are actually punched into it. This is the guy you're going to run into most often. This is called an incremental encoder. Yes, but they call it an absolute encoder, but it's not. This is what robots use there. Most robots. I don't know of any that use absolute encoders. So what we do here is we have blades that pass between these optical sensors, and then all we do is just count the blades, right? You understand? So this would have Let's count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing 10, 11, 12, 13, 14, 15. Now what we would do is we're going to take this out, the output of this thing, which is going to give us a series of pulses. And then we're going to run that into a binary counter. So what sets the resolution is not the number of petals you have per revolution. It's how far these dang counters can count up to. That makes sense? So now all of a sudden I've got one encoder. I've got an electronic circuit called a counter. All it does is just count pulses, and then over here it would give us a binary number that represents the count. So if I've got a 10-bit counter, it's about 0 to 1023. It don't make any difference how many petals you have. But once it got to 1023, what do you think it would do? It would roll over, yeah. Just like the old numbers on the car used to do. Could be laser. Don't really have to be. It depends on how big the petals are. It's usually going to be a light that we usually can't see, even though I did that. But all we have is we have a transmitter, and we'll talk about these later on, and then we have a receiver that's sitting there picking up the lights. And y'all run this into it all the time, right? So where do y'all use something like this at? Yeah, these are light transmitters right here, and then there's a light receiver up there, and we're shooting a bunch of pulses, different pulses, and then the little processor there decides what size pulse stream you get would be whether you want to change channels or whether you want to increase the volume and stuff like that. Sort of, but we're actually sending the pulses, which would be basically, this guy actually sends it, but this guy, we would actually have a counter that would actually count the pulses, right? Now what the problem with this guy is these counters are going to have to be powered. These are electronic circuits, they have to be powered. So what happens if we lose power to the counters? Well, if you lose power to the system, you lose your position. So that's why robots have batteries on them. So robots have batteries on them. So they look like they're absolute encoders, but they're not. They're incremental encoders, but the counters are part of them. But the problem is if you lose those batteries on that robot, if you don't keep them up, you'll lose we say we lose the origin. The robot don't know where it's at anymore. And you have to re-origin the robot. Most of the robots have marks on them or something that you do where you line them up and you say, okay, this is equal to 0. So they are absolute encode. They're technically called battery backed up absolute encoders because they're actually incremental encoders, but they have the counters as part of the encoder. So the biggest problem we have with incremental encoders, if you lose power to the system, what do you do? Yeah, or you find it. So it's like anybody got a print? Y'all got a dot metric? Y'all got a inkjet printer at home? It uses these guys right here. But when you turn it on, what do you hear it do? Yeah, well, it's got a sensor on one side. It goes there and finds that sensor, and now it knows 0. It does that one time, right? Or if you have a jam, if you ever have a paper jam, it gets all messed up, right? So yeah, those guys are using incremental encoders, and so it has to do what? It has to find itself every time. So the biggest problem we have, of course, for these guys is that if we don't lose the count, then we're going to have to keep power on the watt. Counters, yeah. Anybody ever took any robotics classes over there? I think, yeah. So all your robots over there, all the real robots have a little slot on it where you put batteries in. And what that does is in there to keep power on the watt. Counters, yeah. So this is an incremental encoder. In fact, this is an incremental encoder off one of the printers that we've got around here somewhere. This incremental encoder kept up with the position of the paper. This is the old mouse. So here's the old mouse. Here, what type of encoders? Can y'all see them? The incremental encoders. Here's actually the sensors right here. So it had a light sensor that was in between. Here's the actual left and right button. And basically, when you turn the ball, it either moved this one or that one. If it moved both of them, then it did the math, right? To calculate with them. Don't get the ball get dirty, right? Or also, what would happen is these little plastic rods would get goop on them too. So you'd have to have a little door on the bottom, you pop it open, and not only do you need to wash the ball, but you also need to clean all these. We still basically use this technique, but what they do now is they use what we call a definite reflector. It's really neat, and they're actually looking at impurities on the surface of your table, which is pretty neat. Don't work on, yeah, over there in H107. We used to have desktop computers over there, and the grain on that thing was real weird, and they would get messed up all the time. So the guys used to use incremental encoders. Well, what we're going to show y'all is something we call a quadrature encoder. So the problem with an increment encoder is something like this, is we have no way of knowing which direction to count. And a robot not only can do what? Can go this way, but it can go that way. Now, if all it was doing was counting blades, it would just count blades. It don't care if they're doing what. It don't care if they're turning in this direction or that direction. So that means when they came up with these incremental encoders where we needed to know the direction, they had to come up with a method so the encoder could tell us which direction it was turning. That makes sense? So what they did was, and this is the primary thing, they come up with what they call a quadrature incremental encoder. Yeah, this is what we'll look at. We've got this. And this is what's on the manufacturing line over there. So notice we have two light sensors, but they're all set by what? They're all set by 90 degrees. So when one's fully exposed, the other one would be what? Would be partially covered, right? Does that make sense? So what happens if it's turning in this direction, right? Then it's going to see one of these first. So what happens is that the pulses are going to be 90 degrees offset. So if we call this channel A and channel B, the direction it's occurring right now is channel B occurs before what? Channel A. And if it turns the other direction, then what happens? Channel A occurs before what? Channel B. So all we have to do is count one of them. We don't have to count both of them. We can count one of them, but we have a circuit that tells you what. So if A leads B, it's going to be turning in one direction. If B leads A, it's going to be turning in one. The other. So this is basically what we use on any device. It's got to give us a what? A direction. So this is what the robots have on right here. They have these quadrature encoders. So if it goes one direction, it might count up. If it turns and goes back the other direction, it would do what? It count down. The count would give us the direction, right? This would give us the direction. The count would give us the what? The position. And the rate of the pulses would give us the what? Speed. So with these guys, we can measure three things. We can measure direction, speed, and we can also measure position. So on the robot, they don't have any special speed sensors out there. But when you deal with what we call a linear or circular move, you specify the speed of the center tap, and you might say the tool center point. You might say I want it to move 100 millimeters per second. Well, how in the world does it know the speed? Well, the controller is looking at the rate of the pulses coming back, right? Does that make sense? So this is what's nice about these incremental encoders, especially quadratures. We get three informations off that encoder. We get what? The position, the direction, and the what? Speed. So this is what the robots have on them right here. If I've got something that runs in one direction, I don't need one of these guys, right? I could use just a standard incremental encoder, because now I've got to have a circuit that does what? You know. By the way, most of your program controllers now, you use two inputs, and it does all the math for you. It does everything for you. So most of your new PLCs handle program logic controllers have inputs that handles these quadrature encoders directly. So you don't have to really do anything. It'll give you the direction, it'll give you the count, it'll give you the speed. So this is the way we get, this is the signal discovered here. And it's using Hall effect for the encoder. We'll look at that. That's one of the things that sense a magnetic field. So what happens is this thing is turning, the poles are constantly changing, and then we have a sensor that picks up the magnetic field. Now this is going through a gearbox, guys. So this is the drive out here, and I think it's a. So we're only doing one edge, 64 pulses per revolution, and falling edges of both encoders, and we'd have 8,400 pulses on there, but we're not counting both pulses. So let's see, 16 pulses per revolution if one edge. Okay. Let's see if we can see the math. So we're looking for the gear. Oh, it's a 131 to 1. So that means my motor's turning 131 times for one revolution of the shaft. So we have 16, back here on the motor, we have 16 pulses per revolution. Then it say 16 pulses per revolution if we only count one edge. And then I would multiply that times 131, and that would give me my pulses for revolution of the shaft right here. That's pretty good resolution. What does that come up to be? Well, back here on the motor we have 16 pulses per revolution. But the problem is I don't want to know the speed of the motor. I want to know the speed of this output shaft right here. Right? You understand that? Well, this is going through a 1 to 131 gear ratio. So that means this guy here would make 131 turns for every one turn of the motor. I'm sorry, this guy, the motor would make 131 turns for every one turn of the shaft. Okay. So how many pulses would I get per revolution of the output of my shaft? Is that what you got when you took 16 and multiplied by 131? So what did you come up with? 2,100 per revolution. This is not exactly, this is the spec right here. I don't know where they got this. So this is the gear ratio. This is the gear ratio, 131 to 1. Okay. Then I'm going to multiply that times 16. 2096. So that means we get 2,096 pulses for every revolution of this shaft ring. Okay. For one revolution. So this is the output right here. Let me switch back over to my camera and show y'all the direction. And I don't know why it's not zooming in. Let's see if we can get it to focus a bit. Yeah, this is a digital oscilloscope. And I've got them on top of each other. Y'all can see the different colors, right? Yellow and blue. So right now, blue is leading yellow because blue occurs first, right? That's it. Now I'm going to change directions. So what we should happen when I change directions, we should see yellow lead blue. So now yellow is leading blue. So this guy is turning counterclockwise. So now I know if yellow leads blue, it's counterclockwise. If blue leads yellow, right? Okay. And what we could do is and this is what they were saying. I could count both. If my counters could count both of them, then that would be 32, right? You understand? If we tried to count, if we had counters that could count both the rising and falling one, then we'd have 64. But normally counters don't do that for us. Are we okay? This makes sense. Okay, so how fast is my motor going? So what I'm gonna do is I'm gonna get rid of the blue one and just put the yellow one up here. Okay. So somehow we should be able to come up with the speed, right? What's that? No, this is a cycle right here, and yeah. Well, you count the time for the cycle. So the time for the cycle would give us the okay. So I have it on 250 microseconds per division. Let's see if I can go down one time here. I don't think I can. I think that's the best I can do. What's that? Yeah, but we don't need the time for two. All we need is the time for one. And the motor's not running real smooth. But so 250 microseconds per division. I got 1, 2, 3, 4, 5, 6, 7.8 divisions. So you're trying to figure this out, right? Yeah, per division. We got how many? 1, 2, 3, 4, 5, 6.8 divisions. Can you see me counting? 1, 2, 3, 4, 5, 6.8. 1, 2, 3, 4, 5, 6.8. Yeah, it can't be 2 micros because we're multiplied 2 milli. Where'd you get at? You got it? Huh? 2 milli? I can't multiply 6.8 times 250 micro and come up with 2. 6.8 divisions. 250 microseconds times 6.8, 250 micro times 6.8 divisions, right? $1.7 million. Yeah, but we need to keep this pretty accurate. So 1.7. Let's carry it out to 2 decimal points. 1.7. Okay, 1.7 million. Okay. So what do we need to know? So that's the time it takes for one pulse, right?
What would be measured in?
Scopes measure in time,
So it'd be milliseconds.
in milliseconds. Scopes measure times. And that's what this is. I don't know if y'all can see it. I know it's not. But this is microseconds. So that's 250 microseconds per division. And we measure volts this way. So to measure volts, I'm going to get my thing on a solid line. And we have it on 2 volts per division, so that's 5 volts right there. So this is a 5 volts pulse, right? Everybody okay? Makes sense. So guys, what do I do now? So that's the time for one pulse. So what would be the time for revolution? So that's the time for one pulse on this guy. We're trying to figure out how fast this guy here is turning. Excuse me? Oh, you want to go back to the data sheet? Okay. So we're only using one edge, right? It says if you count both edges. If you count one of them, it's what? 16. And we got a gear ratio of 132. We're trying to find the speed of the motor. And how do we give motor speeds? They're in how fast the motor runs. We call it what? RPM, revolutions per minute. So we're trying to go from time to minutes, right? I mean, we're trying to go from seconds to minutes, number one. So what do you think we need to do next?
Multiply that times the gear ratio.
Times gear ratio, right?
So your TF is 1.7 times the I multiply 1.7 milli times 131, and I got 222.7 milli.
Okay.
Multiply that times, what, 16? 16 volts?
No, we're not doing volts. Speed is in revolutions per minute. It's nothing to do with volts, right? You understand? Well, we can do it different ways. Y'all heard what Brian did. First thing Brian did is he took the time and multiplied it times 131. Why did he do that? Because of the gear ratio. And what did we come up and get? So that's good. All right.
222.7 milli.
So that would be what? No, not yet. Well, we ain't got the TF. We could come up with a transfer function, but we hadn't done it. We're just working our way through it, right? Okay. So that's in. So we got what? How many milliseconds? I mean, now. What's that? That's the first one, right? Right. Yeah. And then we multiply that times the gear ratio, which gives us what? Milliseconds, right? Okay. Okay. Milli, that's, what's that? 250? No. Per pulse. Per, yeah. Okay. So good so far. What do we need to do next?
Multiply it by 16.
116.
Scroll up. I just want to see the number.
No, we did that. That's what we did when we did the yeah.
So we don't use 17.
Okay, so now we've got time. We got it in. I need to be writing these down. What's that? Oh, dang it. Oh, there he is. So first of all, we took what? We took the, what did we start? 1.7 milliseconds, right? And then we multiply that by 131, which would give us the time on our output shaft, right? And what do we come up and get? So what's the next thing we're going to do? So that's the time for milliseconds, right? We could convert it to minutes. What would I do with that? How would I? So we could multiply it by 60. And what does that give us? Now, y'all doing good. Y'all doing really good.
I got 79.51.52.
5.2 what?
No, minutes.
Dang it. I erased everything. What did we come up with? What's that? We multiply by 60, right? What's that? Oh, 0.7. Thank you. What do we come up with here? 13 point what? Any fraction? Thir- yeah, but what's the unit?
Minutes.
We're not doing something right. Because it's not going to take 13.30 seconds to make it. Because then this is still in minutes, right? Oh no, I got to think about this.
I mean, I was looking at the equation right there in blue. It said measure the time for one cycle.
Where?
In the blue. It says, number one, measure the time for one cycle.
Oh, this is my instructions, by the way.
That is your instruction.
Yeah,
That's
these are
why
my.
I said you be trying to be slick. And you forgot your slickness. Look at this. Come on, Rick. What you claiming?
Measure the time for one cycle, right? Multiply the times by the number of pulses per revolution. Okay. Take the reciprocal of the number, right? which turns it into what? It does say receptacle? Okay, you're right. Reciprocal. It always amazes me how many times you could use something and then nobody says anything, and then all of a sudden they do what? Somebody brings it up. So that's supposed to be reciprocal, guys, not receptacle. Reciprocal. That's not supposed to be receptacle. It's supposed to be reciprocal. I can't. Right. Per what? Per second. Right. Everybody okay? So what we're doing is we're going from time to frequency. Everybody okay? So how fast is the motor going if you use reciprocal instead of receptacle? Yeah, what happens? We missed this. We were trying to multiply by 60 before we got it into seconds. So what we're doing is we're going from time to frequency, right? So we have to take the reciprocal of that. 4 point, is that a whole number? Yeah, we're still not doing something right. Yeah, so that's still not right. Yeah, mine is too. Take for
Measure time for one cycle. The time we got for one cycle was that
1.7. Yeah. You okay? Okay. Yeah. So we measured, what was our time? 1.7 milliseconds. 250 microseconds, right? Okay, so that would be the time for one pulse, and we get 2,100 pulses per revolution. So this should give us the time for one revolution, right? Multiply the times by the number of pulses per revolution. Right. 1 inch when we count per revolution on the output shaft. Right. And this would give us, by the way, this is the way so measure the time per cycle. We know that's what? Milli, right? Everybody agree with that? And then we'll multiply that times the number of pulses per revolution, right? Guys, this still is not going to work out right. So what you got? And this would be what? Seconds? Then we take 3.557, right? 3 points, and then we take the reciprocal of that. $208.80. And then we'd multiply that times 60. This is right, guys. We got it. $16.8 revolutions. I'm having problems with my thing. Revolutions per minute. So how many revolutions would I have? How many revolutions would I have in half a minute, 30 seconds? Yeah, we'll oh, I know what's going on. Hold on. So somebody give me 30 seconds. Tell me when 30 seconds is over. Y'all got a timer on y'all's phone, right? Tell me when to start. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, about 8 revolutions. What we calculate? RPMs? Huh? 16.8 revolutions. We wasn't going to go a minute. So we calculated the speed of this shaft, right? Wasn't that cool? Once we finally did it right. I'm sorry. And you can't turn this with your hand because you got it's got 131 to gear ratio. So this guy puts out 131 times the torque that this little motor's putting out. So what happens when you increase torque, you decrease speed, right? So this right here is definitely a torque multiplier. No way in the world I'm going to stop that. Wasn't that neat? We started off by reading this, then we did the math. We calculated 16 point, and we come up in, when we actually measured it, sort of, we got 8 point something revolutions, which is what we calculated. Pretty neat. So what can I get off this thing? I could get position. If I counted, I could get position. since it's a quadrature encoder, I could also get what? Directions, and I can also calculate what with this, with speed. So this is the advantage of these quadrature encoders. Incremental encoders, we can get counts and we can get speed. Quadrature encoders, we can get counts, we can get direction and speed, right? So I got one sensor that gives me multiple things. So these are, as far as position sensors, guys, these guys right here, and they give me a digital output, right? You understand, ones and zeros. My PLC could count that, no problem at all. That's one of the things PLCs do, is count. And then I could run it through this little math instruction, right? And we could come up and actually get the speed and also the direction. And like I said, most of your PLCs, they have counters in them, and they have quadrature encoder counters. So we just bring the two inputs on this thing into the PLC, and it would count up and it would count down, and we could also count. We could count over a certain time, right? You understand? And then use that to count and use that to calculate speed. So, any questions? So, yeah. Yeah, that's it for today. I got to do something today. What are y'all gonna bring in? I'm going back. What's that? Now bring your multimeter in. We're gonna do a lab on potentiometers. We'll probably go over to 206 because that's where all the trainers are at. We're gonna start over here, and then we'll move over there and we'll do a lab on potentiometers. So we could calculate. So what do you want? What did you want, Jacob? You had a question? I don't think I did. This is the procedure right here, though. Oh, I could edit that from here. You do? We were close. It's just that what we did, we didn't convert it to seconds before we multiplied it by 60.